connected to today's seminar. Actually, our speaker that we'll introduce in a second was a friend and collaborator, Dr. Atindra Mitra. And so the Dr. Atindra Mitra Graduate Fellowship in Electrical and Computer Engineering was established in February 2012 in the memory of Dr. Atindra Kumar Mitra, who passed away on June 15 in Dayton, Ohio. Atindra received his PhD degree in electrical engineering from Texas Tech University in 1996, and his doctoral work was completed under the advisement of Dr. Thomas Strossen, who's actually in the audience. And I remember him as a student as well. I came here in '86, so his doctoral work was completed and it focused on statistical characterization of small microwave reverberation chambers. He also received his Bachelor of Science degree in EE and Master of Science degree in EE degrees from Texas Tech. And Atindra worked at Advanced Micro Devices and held teaching positions at the University of Nevada at Reno and the University of Dayton in Ohio before his 12-year tenure as a radio frequency systems engineer at the Air Force Research Laboratory at Wright-Patterson Air Force Base in Dayton, Ohio. I've been there personally myself several times. While at the Air Force Research Lab, he was at the Sensor Technology Division. Atindra authored and co-authored several patents involving innovative radar system concepts. Atindra was also the founder and director of the Air Force Research Lab Radio Frequency Systems Integration Laboratory. His research interests included unmanned aerial vehicle applications and distributed radar systems, radar waveforms, signal data processor hardware design and architecture, and radar and sensor networks with adaptive intelligent processing. Atindra was born on August 23rd, 1961 in Calcutta, India, lived in Marburg, Germany until age 5 and spent the rest of his childhood in Lubbock, Texas. He was an accomplished classical violinist and enjoyed many other interests, including golf, basketball, traveling, and algorithmic day trading. Friends and family remember his creative, unorthodox, and insightful opinions on a wide variety of topics and his gentle and compassionate nature. And so the Dr. Atindra Mitra Graduate Fellowship will be awarded to PhD students in electrical and computer engineering who have an interest in Atindra's research areas, including smart algorithms design, detection of obscure targets, and spectrum analysis for adaptive systems. I'd like to add, we all owe this to a generous donation from our esteemed colleague, Board Professor Dr. Sunanda Mitra.
Let me now introduce our speaker for today. We have Dr. Roscoe Cermak from Louisiana Tech University. He obtained his bachelor's degree in electrical engineering at the University of Belgrade in 1994. Then he came to Texas. He graduated from UT Arlington with his master's and PhD in 1997 and 2000 respectively. Currently, he is an associate professor and AT&T associate professor in electrical engineering at Louisiana Tech. He was Air Force Research Laboratory Fellow during summer of 2007 and 2008. That's when you met Dr. Atindra Mitra. And Dr. Cermak's current research interests include intelligent sensor networks, smart sensors and actuators, intelligent control, and fault detection and nonlinear systems. He's the co-author of 1 US patent with 2 addition reports of invention, 50 journal and conference papers, 3 book chapters, and the book Neuro-Fuzzy Control of Industrial Systems with Actuator Nonlinearities. Let's welcome him and give him a round.
Thank you very much for the introduction. It is a pleasure to be here at Texas Tech University. I dedicate this talk to Dr. Atindra Mitra. I consider myself to be a good friend of Atindra's. I spent some time with him at Air Force Research Lab. And later also he visited Louisiana Tech a few times. I visited him here at Dallas, Texas. Sorry, we have problems with Mac and the PC. The projector didn't like Mac, so we need to switch PC. So as you heard, Dr. Mitra graduated with master's PhD degree from Texas Tech University. He was founding director of IDCAST lab in Dayton, Ohio, that supported research and some commercialization work in Dayton. His interests were in UAVs, micro vehicles, radar systems, sensor networks. I will talk about some of the projects that are related to work between me and Dr. Mitra, such as position adaptive direction finding. Then I will talk about some navigation and control algorithms in sensor networks. Then overview of some existing projects and some future research. This is the overview of our group. We conduct the research in mobile sensor networks using micro vehicles. Atindra influenced that work quite a bit. Then we work on coverage control in wireless sensor networks, optimal deployment, gesture-based computing and control, that's something new. These are our group members. We work with Christian Duncan from computer science, Jim Kokana from math, Jeffrey Walton from psychology department. My group has 5 PhD students, 2 masters, and we always have 2 undergrad students. That's the way to basically recruit students into PhD program, at least in Louisiana Tech. We're a much smaller school than Texas Tech. This is first lab. It's mostly controls lab. We have standard controls modules, 2 mobile robots here, standard inverted pendulum module, flexible link, mostly for undergraduate system classes. And this is 2D helicopter example that is more for research. This is the new lab that we developed, funded by the Air Force Research Lab, partially at AFOSR. We developed indoor GPS system using these Vicon cameras. Really came from Hollywood industry. They are putting the markers on the robots in Hollywood movie development. They put the markers in the human body. And then as people move, then you detect very accurate movements and put this different software to develop very accurate representation of human movement. Now we use this for robotic control. All these micro vehicles are equipped with a little wireless sensor nodes, and that represents a platform for mobile sensor network. Besides that, we have a static sensor, so together it's a complex system of static mobile sensors. This is something similar that the Air Force has, and I will mention differences between their lab and our lab. We consider our lab now one of the most state-of-the-art in the nation, or around the world. There are few universities that have this, but there are some unique aspects of our lab as well. I like to give credit first to my students, and that's our research team. PhD students, Ray Zhang, works in coverage control, sensor networks, and fault detection. Miguel Gates, sensor networks, localization, cooperative control. He spent 2 summers in the Air Force Research Lab, and just as an example how Atindra was a very nice guy, he lived a very humble life, but I didn't know. I asked my student after some time, okay, did you find accommodation in Dayton? Where do you stay? He said, no, Dr. Mitra, and he did not work for Dr. Mitra at that time. He said, Dr. Mitra offered me to stay with him. I will stay with him. He offered me his place, he feeds me. He said, he's really very nice guy. I said, oh, yeah, I know. Chris Barber works on laboratory development and cooperative control. Del Jackson on coverage control and gesture-based computing. New PhD student, Salva Ramazani. 2 master students, Abhilash Talapalli and Jeff Lee. And undergrad student, Andrew Gardner. We now have another one. Again, Andrew is continuing to the graduate school. So this is our pipeline and a vehicle. Recruit first good undergrad students, and then keep them in a graduate school. This is our research team. Sometimes people say, oh, we collaborate with this and that, but with these 3 people, we really meet twice per week, work together on projects, and that resulted in some of these achievements that we have. Dr. Reddy is in nearby university, so we don't meet with him every week, but he's a member of our team as well. So the way me and Atindra started working is, I was at the conference, and there was a problem in southern Louisiana, a lot of chemical plants, how to monitor chemical contamination so that you don't disrupt the plant. And I suggested to that conference, maybe a little crazy idea. I said, why don't we put some sensors on a little blimps? Because you can't put them on really on the robots, you can't go on the ground. These chemical plants are a total mess. Put them on a little blimps, scan the plant for possible contamination cloud. So Atindra came after that and said, wow, that's a nice idea. Why don't we try this, but just with the microwave vehicles? So we put first a microwave vehicle with a chemical sensor nose, if you will, extended on a carbon fiber glue here away from the motors so that we reduce electromagnetic interference. And the heart of the wireless part is here in the middle, as well as the control of this quadrotor. And this would be the movie that it won't work on a PC. I'm sorry, I apologize. I had it on the Mac. Basically, you will see this is an Air Force Air Vehicles Directorate lab, unique in the world with the largest number of these high-speed cameras. You can control any vehicle with a precision of 1 or 2 centimeters. So it allows us, basically, in the movie you will see that our vehicle is sniffing the box for potential chemical contamination. Of course, in the future, that can be explosive detection as well, which we didn't have a sensor at that time. We were detecting carbon monoxide and nitrogen dioxide and things like that. There are several labs, and the Air Force also had even better vehicles that they're playing with. That's their job, navigating, developing the vehicles to have precise control. But what is unique here is that we're combining sensing and control. So the vehicle would go towards the larger value of what is sensed. So you need to combine and develop a system where you have simultaneous wireless sensing and control. So one of the patents, basically, of Atindras was position adaptive direction finding. If you have electromagnetic source hidden in this room, develop the algorithm such that you can deploy little flying birds and that they would locate where that hidden emitter is. And the formal formulation is here, given the number of mobile nodes, maximize the probability of detection of hidden electromagnetic source. We use received signal strength, even though there are other methods for detection. And then we calculate estimation of where basically localize the source. Graphically, this is the problem. If you have some obstacles, you hide the electromagnetic source, you deploy the birds with the sensors to find the hidden node. All nodes can have antenna with different patterns. Right now we consider only directional, but in the future you can have antenna with the specific patterns and use the power of many. When you have a sensor network, instead of having one antenna, you have the power of many. And if you can use that in some smart way, you can achieve much more than with a single agent, as they call it. So approach is to use a received signal strength. The modern radio and wireless sensor nodes can measure received signal strength. Texas Instruments chip can do that, other chips can do that. So you basically receive the signal and have some rough estimate how far the transmitter is. Of course, if you have uniform environment. And this is the basic mathematical formula, and you can find the distance. And then you do least square estimation from the multiple measurements. So this is really nothing new, and you estimate where the location is. The hardware we needed to, we used off-the-shelf Iris node. Needed to modify to make it only directional because the flyer can move in any direction, so we didn't want to be affected of specific directions. And then we integrated this with a Quanser cue ball and put the sensor on the cue ball. After initial funding from the Air Force and AFOSR, this was in our old building, initial lab setup with high-speed cameras, 350 frames per second on a high resolution. They can detect up to a millimeter movement of these nodes. Actually, they're so accurate. If you put the flyer on the ground in the middle of the room and you hit the floor, the little oscillations you can see on the screen. So it's that sensitive. But there is a reason for that, because only with that high sensitivity and accuracy you can use such a system for stabilization in the flight. In the future, that can be used for developing of microwave vehicles with the flapping wings and layer sensing concepts and a few things that I will mention later. This is my student flying one of the cue balls, and the next slide would be simultaneously flight. We were the first at that time to develop the cue ball flight with the sensors, simultaneously two of them. If you watch YouTube movies, there are multiple. Penn State has a nice movie with the small flyers, large number of them simultaneously flying, but they don't do sensing and control at the same time. So the system looks like this. Antenna is moved again from the motors towards the bottom. After some experiments, we realized that that's the best position. While the sensor node is in the middle, there is on-board computer for flight stabilization. And this node communicates with other static nodes around the room through this wireless antenna here. Data flow is something like this. Data comes from Vicon cameras through the Ethernet switch, and then it's fed towards the flyer to inform it where it is. Flyer compares where it is and where it should be, which is assigned by the user through the MATLAB interface, and that creates the error, and LQR control inside adjusts the error. Based on that error, adjusts the flight and stabilizes the flight. We experimented with different setups with obstruction and without the obstruction. This is the hidden node. These are the static nodes. All of them have some error when they detect signal strength. So you really have the estimation is intersection of these disks. And then other sensing topologies, moving some of these quote-unquote friendly nodes in front of the flight, in front of the hidden node, and you will see the reason for that a little later. We also then gathered some data to see what would be the decent and good distance between hidden node and the receiving nodes for relatively accurate estimation. And that would depend on the radio strength, on the type of protocols that you use. For this Iris node that runs Zigbee protocol, that was the distance here between 6 and 8 meters. Then we put some obstructions to make the problem more difficult. And configuration 4, which is this one here, has the higher accuracy because you will see in the next slide we put the box around the node. So Atindra was saying that we need to consider difficult problems, not the emitter that is middle in the open space. We want to do something to emulate urban battlefield scenarios so that the hidden emitter is hidden in the building with some windows. And this is a window, and the hidden emitter is in the middle. So how to detect it then? And there were several approaches. One of them to put static nodes around, and then to have mobile node basically circling and detecting where the signal is stronger, and that would be the area of the window, and then to go into some zigzag pattern and do estimation online all the time. This is a little too dark on this screen, but it's a setup at the Air Force lab. The box has aluminum foil on all sides, which really cuts down on electromagnetic propagation significantly, so makes the problem much more difficult than if you have the emitter in the open space. And then we have some RC vehicles and a little helicopter that can circle around and estimate the position of the node. Here is the helicopter in flight. It has also wireless node that communicates with other static nodes, and this is like a ground vehicle. And then with the microwave vehicle, the math can go into this zigzag pattern, and in the zigzag pattern to online estimation. This is a slightly better picture of the experimental setup. At least you can see the box a little better. All these vehicles have these little markers that are observed by the cameras. You can see only one part of the cameras. There are 64 cameras all around the room. In our lab, this is the setup that we came up with, a bunch of static nodes. Here is one flyer, the box with aluminum foil and the hidden emitter inside. Now I must say we started with a problem that is relatively, even this for us was difficult, but relatively easy, that the hidden emitter is a member of the network. We know what hidden emitter is. We know that that is Zigbee protocol. we bought that emitter and we hide it somewhere. That is still a challenge to detect it in difficult environment. Some experimental results, we measured the accuracy. This is the error, is a red line, and then the metric we try to develop. In real life, you don't know what's the error, but you can only think about what is the metric. Metric, we measure the uniformity of the environment between the static nodes. And if the environment is uniform, and we do that by measuring cross PLE path loss exponent, then we say, okay, it's very likely that we're going to have high accuracy. If not, then the accuracy is not going to be that high. The metric was somewhat correlated to the error. But I must say that requires still more work, and we're working on that feedback concept. This is our new lab. Louisiana Tech developed a new building for cybersecurity, and we've got a fancy lab there with different micro vehicles, static nodes, ground robots, and things like that. So some discussion and future work. So we performed some basic localization experiments, both at AFRL and Louisiana Tech University Mav Lab. Now, we would like to include some new ideas, and that is related to subsystem analysis as a feedback for Mav configuration. And I'll talk a little bit more about this. I must say one benefit between AFRL and University Lab, and I spent there some time, the Air Force, for all different reasons, security reasons, is very bound by different bureaucratic issues. For everything that you need to do, you need approval for this. You want to install the MATLAB? No, you cannot install on this software, on this computer. Well, we want to install this, no technical personnel needs to install it. You need to write the request for it. You can install in 4 days. And so that whole thing is slowing down not only us, but their researchers. So now that we build this lab and universities are operating a little more freedom, it was an awkward situation that we had a few times Air Force people, Indra came twice, and a few other researchers, Sean Young from the Sensors Directorate, and another lady. Now they want to do some experiments at our lab because no paperwork required. I don't know, that has a good and bad side, but we have now that university freedom and a fancy lab that we can do experiments with not too much of approval. Now, Atindra suggested one, I think, brilliant idea, and he had many brilliant ideas. That's why I consider him really a brilliant man. Many of these ideas are way advanced, and his way of thinking is he comes up with an idea and he sees it. He doesn't write it on a paper, he doesn't go into theoretical development, and even doesn't go first in an experiment. Then he would go to experiment. So he says, why don't you try Cepstrum-based feedback for adjustment for control of micro vehicles? And I barely heard for Cepstrum, so I asked him, well, what is that? You know, I heard that music people use that, and people who deal with amplifiers. He said, that might do it. You go ahead and read it. That might do it because we all have this built in ourselves. This is in nature. This is method of survival. I was shocked, you know, when he said this. So I studied a little more. Sure enough, there is a story behind it. So the Cepstrum is really like a Fourier transform of logarithm of a power spectrum. But basically, if you have echo, if you have a large echo, then your frequency response of the signal would be wobbly, and then when you take FFT of that, you will see a spikes, which is called Cepstrum. You will see a spikes on that specific wobbly frequency. So really, Cepstrum gives you a measure of echo signal. So then I later asked him, well, why is this in nature? What do you mean? If you go and search in Google, you will also read what I found. We have capability to distinguish if we are talking close to the wall, if there is echo, or if we are far away. If we are close to the big animal or a big obstacle, through evolution, we developed the thing that we can distinguish if something big is close to us. And Atindra said, why don't we use this as a measure to run away from the areas where there is a large echo? Why don't we use this as a feedback concept? And then later I talked, now I heard a little bit about Cepstrum after all this reading, but I can tell you, Atindra, I've never heard anybody using this as a control method feedback. I mean, I've been on many conferences by now. Nobody ever does this. So now this is a future theoretical study. I instructed my students to study this. Have multiple vehicles. You need to process the Cepstrum level and try to reduce those peaks, basically moving away from high echo environment, which will in turn give you a good estimate where the hidden source is, which I thought was a brilliant idea, combining something from something totally irrelevant to this problem. And we want to go a little further now. We would like to develop a sensor node that can be used as a primitive spectrum analyzer in a distributed way, that we can have a sensor node that can scan for different frequencies. So why do we want to do that? Remember, as I mentioned, we started with the nodes that we know what is it. We hide the node. But the Air Force and Department of Defense is very concerned about what if enemy hides a sensor node in this room of their own protocol, their own frequency of choice. We won't find it. We will not be able to know where it is. We will not be able to locate it that easy. So we need to have a sensor network that will be able to scan different frequencies, and that really relates to software radios that are still on a little high form factor, but they're shrinking down. When that comes to the very low form factor, I can envision in 5 years having a little sensor network of software radios that can scan different protocols and different frequencies, detect even unknown, completely unknown nodes. So we started with something very simple. We don't have that, but we started now building a sensor node with 2 receivers only that will scan 2 sets of frequencies. And some antennas, in this case we chose 4 antennas, and my students are right now simulating antennas. We are not, I myself are not expert in antennas, so we need some help on that. We designed a node that can have electronic beam steering and switching to different frequencies and sniff around for enemy node of still relatively known frequency. But basically we're reducing the assumptions of that we know what's hidden. Now we don't know completely what's hidden, but we know, okay, few frequencies. Ideally in the future, we would like to scan over broad range. And then again, put that on our microwave vehicles and have different antennas that can search for a hidden node. A few words about another project, and that is navigation in coordinate-free and localization-free sensor networks. Sensor and actuator networks, in this case we need some actuation. You can navigate the robot if you have a GPS or if you know where you are. But if you put a robot on Mars or in on Earth, somewhere where the GPS is denied, or during a war GPS is destroyed, GPS satellites are destroyed, then many of the navigations will get quite tricky. So we are interested how to do that using sensor networks. The original problem for us comes from if you have a sensor network and a hole in the network, how to navigate the robot to patch the hole, provided that you don't know exactly where are the nodes. But what you do know is who is communicating with what. So you have hop distance relationship. I am one hop away from this node, one hop away from that node, one hop away from that node. So if I need to go from node 0 to node 43, I need to look at what are the one hop less and progress that way. And that's basically the algorithm. So the first thing you need to do hop assignment. If you know where is the target, you need to go and fix something at node 43. Well, 43 is one hop away from node 37. 37 is one hop away from 33, and I'm one hop away from 33. So I need to go this route and come to the node. To move the object, in this case ground vehicle, it can be in the future in three-dimensional space micro-air vehicle, you need to have actuation signal from 3 nodes. It can theoretically even go to 1, but there are some benefits to 3. Form the potential field, go to the minimum of potential field of this triangle, and kind of park there, then go to the next triangle, next triangle, next triangle, and travel to the sensor network in that fashion, without precise locations of the nodes. Here is the setup. We have a robot, Pioneer robot with a relatively standard university level, mostly for indoor use. And then on the robot we put the listeners based on Cricket system. Cricket is wireless sensor network system developed by MIT that has capability to precisely determine distance from this and other nodes. Then we place some nodes on the ceiling, that's our sensor network, and the experiment runs that the mobile robots move to that sensor network environment. Also, we built a simulator, one of the first distributed, completely distributed sensor and actuator network simulators. There are many on the market, but very few, we didn't find one open source distributed simulator where every agent you can develop your own code and deploy. We build this now with some certain toolbox capabilities, so we believe in a year or two, this first PhD student is working on this. In a year or two, we might have even a little product on that. Related to micro vehicles and, as I mentioned, layered sensing architecture, we participated for 1 week in something called Tech Warrior Exercise. It's an experiment where we went to this ghost city and needed to do some robot navigation without direct line of sight. We needed to place the camera and then navigate the robot with a chemical sensor to determine is there any chemical contamination. We didn't have explosive sensor at that moment. Alpindra was basically organizing all this. He was so helpful, treating us like his own children there. It's very difficult. We take many things for granted when we do experiment and simulations. And then you go to the lab, experiment, and something doesn't work. Even today, Mac didn't work with this thing. But this place has no electricity, no water, no power, no internet. Then you realize how things are tough. You know, you don't think about, okay, what am I going to eat for lunch? Well, no lunch, no water, no electricity. You need to battery power these things. So we experienced for 7 days some of these military drills there, and it was really interesting experience. I'll remember the rest of my life, I would say. That this is our team. Experiment was successful. We might do it again this summer. So layer sensing architecture is this. You have sensing in the layered concept. You have ground vehicles that are equipped with close proximity sensors. Then you have a little upper layer, it can be these cue balls that are flying a few feet away. They have a little better picture of what's going on the ground. And then you have high-flying UAV that controls the flow situation. Provides communication and control. Up to this year, we had this and the robots. Now we purchased this high-flying, it's not even micro vehicle anymore, it's a UAV. It's robust to fly outside even with some wind, and we plan to use this in the future exercises. We integrated with a camera that can track these vehicles on the ground as well as these smaller micro vehicles. This is something interesting that we started doing, I would say, 6 months ago. And for me, first it was a little shocking, but then it's really developed into something very interesting. So, last few years I worked with the sensor networks. And all these can be considered dynamical elements. They have their own dynamics. They can have failures, and then we work on a failure detection and things like that. But then we found several interesting papers that talk about human emotions. And interestingly, after reading several of them now, I know a little bit, human emotions follow dynamical system pattern completely. If you are happy, if you have a happy shock in your life, you will have a peak, and then you're going to oscillate, and you're going to go down and settle at some level. The same thing if you have a negative event in your life. You're going to go down, it's going to oscillate, it's going to come to the same level. And then the researchers in the last 5 years realized that actually the long-term prison sentences from the point of view of punishing people don't make too much sense. Because those people get adjusted, they're equally happy in the prison after 5 years, three to 5 years they say. It does make sense to protect the society from the criminals, but if we think that we are punishing them after 3 years, then we are not punishing. So why don't we consider the network of people where we have the same thing as the sensor network? You have a base station, provides some control of the network. You have a nodes, dynamical element that talk to each other. And what is the difference between a group of people that can be connected to each other and have a power leader that affects the rest of the group? It is well known that if you are extremely happy one day, then your girlfriend or your wife or your friend, close friend, they might be affected as well. And then they might be happy and pass this to a second hop in the sensor network terminology. Now this propagation will stop after a few hops. That's what experimental psychology says, and even some of our simulations. So we started this research where we want to try to model some emotions using systems theory and apply some of these fault detection results into trying to detect problems in emotional behavior in humans. We try to develop the models for the group of people. Individual models are already known, and we use those results. So Jean-Jacques Fautin from MIT a few years ago proposed a leader-follower network model for mostly for electromechanical systems, where you have a power leader and leader influences the followers. The same as in a group of people. Usually you have a person that is a leader, influences the others. Of course, there are some coupling coefficients between those links. So each of these nodes is dynamical element, and then we first, of course, studied this from electromechanical point of view. You can have different factors affecting either a single source or neighbors and so forth. So the power leader is represented by this dynamical system with external force. This is a state space equation. It can be a general case nonlinear system. F is a general input. It's external force in terms of emotions as well. The followers have the nonlinear element as well, but they're coupled with other followers, states of other followers. And those matrices, you can either assume them known, or extension of the work would be to assume them unknown and apply some techniques to estimate. So we started with relatively simple state space model for the power leader, given here, and you can represent this in a vector form. The followers have a little more complex dynamics. It includes the links with their own neighbors. So we introduced the fault. Fault is a change in the dynamics. Something changed in a system. It does not behave normally anymore. You have the fault in this form. This is the value of the fault and the time function representing how that evaluates over time. And then build an estimator. We decided to build neural network estimator for the leader and the the followers. And when you build the estimator, you measure that with real data, and if they're matching, then everything is fine. If there is a big difference, that's a standard method in fault detection. The scheme for the detection is this is nominal system, nonlinear system, and basically neural network observer. For those of you who took controls classes, that's maybe something familiar. And the same thing for the followers. To develop custom-based tuning law, which in this case we have to, you can't use some things out of the box. We use the Punnov stability. So for those of you who took nonlinear systems class, for instance, you put the Punnov function to guarantee the stability, and you develop the tuning law, which is really, doesn't complicate, but it's not that much. Most of these matrices are constant. You have the state error here, and several lines of extra code, basically. Similarly, you build an estimator for the followers. Right now, we assume the first step that the topology of the network is known. We assume who is connected with whom. In terms of sensors, we assume which sensor is connected with what. Or in the people, we know who are the friends. And the tuning law is given here. The constants, coupling factors, we estimate them. So that was the extension of the work now. So we don't know how well you're connected. We know that you're connected with some other node, but we don't know how well, and we do estimation. And this is just a sketch of stability analysis. I'm not going to go into that, but you basically establish the Punnov function where you weight the errors, where you weight the neural network weight errors in weights, and coupling coefficients. And if you use this tuning law, it can be shown that the system is stable. Some discussion on that. You can adjust the stability radius by increasing